Okay, hello again. Today we're going to talk about a particular aspect of the electromagnetic spectrum, and that's radio astronomy. It's kind of leading up to some of the radio astronomy stuff we're going to be doing in the next few months. So this is kind of a quick synopsis of the electromagnetic spectrum. You can see how waves are long and then go off to short, and you can see that radio is towards the longer end, and then you've got microwave and then infrared and visible, and you can see that the waves get shorter, the frequency gets higher, and you can see the wavelength and the frequency there. So radio is towards the long wavelength, lower frequency end of the spectrum, and it's invisible to human eyes, kind of like infrared, ultraviolet, X-rays, and gamma rays. We only get to see that visible slice where the colors are. But if we want to do radio astronomy or observing of celestial things in the radio band of the electromagnetic spectrum, the radio waves have to penetrate the Earth's atmosphere, the moisture in the gases in the atmosphere. And the parts that can do that are the lower end of radio and the higher end of visible. So that's the areas in the green dotted boxes is where we can observe. And then I put in down towards the bottom the particular frequency. When you see 10 to the fourth and 10 to the eighth, it actually goes up to 10 to the 10th. You don't really get a feel for it. But if I say it's from 10 kilohertz or 10 thousands of cycles per second up to 10 gigahertz, which is billions of cycles per second, then you get a feeling for the wide range of radio frequencies that we have there that do penetrate the atmosphere. So the ones that do make it down, we can actually observe those. And as you get towards that higher gigahertz level, even small amounts of atmosphere can attenuate or reduce the signal strength. And therefore, for those higher frequency in the microwave area, we tend to do those in mountaintops, South America, high plateau deserts, or in rural radio quiet regions, sort of like Green Bank in West Virginia or the VLA and outside of Socorro, New Mexico. So does it take these big dishes to do radio observing? Well, as it turns out, if you want to do the more distant things, the really radio dim things, then yeah, you're going to need something that will draw in more of the photons of radio to gather all that up to make a stronger signal. And when you want to make a big radio telescope, large diameter, to look at details, then you want an array to basically look at a large area of sky, and then you use software to narrow it down and correlate all of the data being captured to get radio images. But sometimes you're just looking for the scientific frequency analysis of a particular radio signal, and then you have that giant single dish there on the right. That's Green Bank in West Virginia. But for backyard observing, you can observe the brighter stuff, the 21 centimeter hydrogen line of the Milky Way. You can see that with a do-it-yourself backyard antenna made from air conditioning duct and aluminum foil. And then you can get a antenna. That's the antenna. And then a software-defined radio that you plug into your computer, and you get some free software, and now you can receive radio signals. Signals, not pictures. So if you look over on the right, that's what you get with your single radio antenna just pointed at the sky. You get radio, you get waveforms, and it's changing in real time as you're receiving the signal. You can't even, it's radio astronomy, but you can't hear it because it's not producing radio frequency or radio spectrum acoustic waves. But you can take the radio signal and make it play like a radio, demodulate it and put it through the headphones or a speaker, and you can hear it, and it just sounds like a lot of that's just the radio noise. But then you can take certain widths of that, certain bandwidths, and see signal in there, and then you can change that digital signal into a color waveform or a color wavy line, or that thing at the bottom that you see the colors in the bright in the center. That's called a waterfall, which is nothing more than the frequency across and the amplitude in brightness, and then it moves up over time. So that's a waterfall. But if you have the array, or if you scan the sky, or you can create one of these very long baseline interferometers and create a synthetic large diameter radio telescope, then you can gather huge quantities of data and post-process process that into an image, and you get, look, there's the plane of the galaxy. So if you're just backyard radio astronomer observing things, what kind of stuff can you get? Well, if you're receiving a signal, you can receive the frequency or the wavelength, which varies over time. And as the Earth rotates or as you pan your radio antenna across the sky, you can see sort of the shape, it being a streak or a round or whatever. You can see the shape of whatever you're targeting. And then you can see the brightness of it because you're receiving a signal that varies in power, varies in amplitude over time. And as you either have the Earth rotate or you pan your antenna, you can see the amplitude of the object. Now, since you're getting the frequency, you can detect, like from the disk of the Milky Way, if you sweep your antenna up here, you're going to see that, oh, that part of the Milky Way is rotating away from us. And then down here on the other end, the Milky Way is rotating towards us, and you will get shifts in the frequency of the 21 centimeter hydrogen line. And that's due to the Doppler shift or the Doppler effect. And that's because the photons are moving away from you. They're being extended and they go more towards the red, or they're being compressed coming towards you, and you get bluer shifted. Not by huge amounts, but by just enough to be measurable. But also, if you're looking at a broad spectrum of frequencies, you can see what wavelengths, what frequencies have notches in them or bright bars in them. Now, these are false color, but you're literally looking at the radio frequencies over a spread, over a bandwidth, and you're seeing how the frequency is either brighter or dimmer or missing based upon the chemistry of what's producing that radio signal. So if you want to observe certain things, you have to know that it's observable with what you've got. And the hydrogen line, the 21 centimeter, that's the wrong frequency. The hydrogen line is something we can use to observe the disk of the Milky Way from pretty much anywhere. And the antenna doesn't have to be enormous and can be inexpensive. At longer wavelengths, at the lower frequencies, you can actually observe radio emissions from the sun and from Jupiter, places like that, just using long wire antennas. You make a dipole, two different sections of wire with the feed in the middle, about 50 feet long, and you can do radio observing that way. Don't need a dish. There are other frequencies that are observable. Not all celestial targets produce a bright enough radio for you to see with your home observatory using a small antenna. Even if you add a low noise amplifier, there are some things like quasars and pulsars that the signal is just too weak and you're not observing all the time. So the odds on catching a fast radio burst or an FRB is fairly low for your average backyard observer. Not all the wavelengths, not all the frequencies can be observed using your $30 USB dongle because it has a range of maybe 10 megahertz to 2.4 gigahertz. Frequencies lower or higher than that might be able to be observed, but you're going to need something that will either down convert or up convert those wavelengths so that your SDR, your software-defined radio device, can receive it. But that's possible. There are a lot of targets in the 100 to 500 megahertz range that are fairly bright, radio perspective, not visually. And you can pick those up. And there are actually a couple of popular catalogs that are publicly accessible. I've got links at the end. One is Cambridge in the UK has a catalog that they periodically will update. So they're up to the an update of the third generation Cambridge catalog, and it has bright radio objects in it. And then the Parks catalog in Australia has over 8,000 radio sources. It's got a really nifty website that you can go in and say, I'm interested in looking at stuff in the, 400 megahertz range, and I need something that's radio bright. So I want a certain level of amplitude in the signal, and tell me about those. And it will tell you the names and catalog identifiers of those targets. And then you can go use your planetarium astronomy software like Stellarium to find the object. And then you can point your radio antenna at that target and receive radio signals from something that's numerous light years away, stuff that you can do with not very much money. So, in summary, radio is invisible to human perception, but using electronics, we can gather data. And the wavelengths, the frequencies that we record from Earth's surface need to penetrate the atmosphere. So, there's some radio that we can't get because it'll bounce off or not penetrate. The things that are persistent, not coming and going, that are radio bright, that have a good strong signal, that aren't spinning or radio bursts that aren't always there, can be seen with relatively inexpensive equipment. The equipment is actually less expensive than, let's say, mid to high level optical astronomy instruments, especially if you put cameras and guiders and stuff on there. Even a single inexpensive radio receiver can pick up stuff, but you're not going to get high resolution color pictures out of it. You're going to get waveforms. You're going to get signals. You can tell the power, the amplitude. By frequency, you can tell something is moving and how fast it's moving towards or away from us. By seeing the signal spectrum, you can tell either what's causing the radio signal or what is being absorbed out of the radio signal. And if you want to do images, there are ways that you can do the Milky Way, the disk of the Milky Way, by letting the Earth rotate while your antenna is fixed, and then you move the antenna up or down, and you create stripes, and then you, in software, glue the stripes together, and you can get a picture of the disk of the Milky Way. Or you can do what I'm doing, which is building a movable radio antenna that carries lightweight antennas, under 20-pound radio antennas. And now I can point them at things in the sky. But that's my ultimate goal of doing all these things. So if you're not familiar with the electromagnetic spectrum, the radio spectrum of the EM spectrum, what radio astronomy is, the hydrogen line from the Milky Way galaxy, what that Doppler effect or Doppler shift is, and then radio spectroscopy as a portion of astronomical spectroscopy. And then the structure of the Milky Way galaxy in radio. You can see where the bright and dim parts are. And then those two catalogs that I mentioned, the Cambridge catalog and the Parkes catalog. So as I said, it was going to be a short one.
There's, we look at the stars, we look at planets, observe galaxies with our eyes, with optical telescopes. To me, it's hard to wrap my head around the fact that beyond my sight, there's still things happening. The radio signals.
Well, there's both low energy and high energy. Low energy would be like infrared radio. Radio can be broken down into microwave, shortwave, long wave, those kind of things. But in high energy, there's X-rays, gamma rays, ultraviolet. There's all sorts of energies in the universe that we cannot perceive. And if our eyes could perceive it, we would get flooded.
So it's real.
Get to see the narrow band.
It's really hard for me to understand. I know what I can't see is there.
Yeah.
And with these machines that look like antennas instead of telescopes, binoculars, and I would have to always convert it into something that I can see.
The wiggly line of a single radio antenna, it's something you can watch change over time. The only way you're going to get a picture out of it is if you scan something, or if you have an array that scans it and glues it all together. Then you can get a picture, but the picture will be in levels of gray. But then you go in and say, okay, if I want to see like something moving rotationally, I will make the colors map onto the frequency shifts from the Doppler shift. And therefore I can see like rotation in motion if I do that over time. But if I want to see just where's the core brighter and dimmer, where are the high radio power signals versus the low power, I can make the amplitude be the color difference. But that's how you can visualize things that we cannot perceive with our wavelength eyeballs.
Intuition wise, you really have to visualize it.
Yeah.
It means changing frequencies and false coloring and all kinds of things.
There was a movie that Scarlett Johansson was in called Lucy, and she got exposed to this particular chemical agent or hormone, and it increased her mental capacity to the point where she had the ability to see in radio, and all of the mobile phones around her, all of everything putting out EM radiation just got visually noisy. And that's probably a good thing that we don't see in all those other wavelengths to keep down the noise. But let's say you were an extraterrestrial from a planet around a red star, a red dwarf, or an orange dwarf. Your visual spectrum may be shifted up towards infrared and have no ability to see blue. So if you came to Earth and you looked in the sky, if you were from the other planet, you would see that the sky is dark even in the daytime because you can't see blue. That would be one of those wavelengths that your alien eyeball just couldn't process. And so it would be invisible, much like radio is invisible to us. It's really a matter of our physiology is rather aligned with what takes place on this planet. And if you go somewhere else, maybe you won't be able to see what the others can see. I doubt that we'll ever visit a planet where people can see in radio but not visual. It would be just very difficult to exist in an environment like that. Not impossible. I just can't conceive of it right now. There are situations where if you turn on your electric stove and you let the element get really hot without a pan on it, you can see the element in red, deep red, and then it gets brighter red. It won't get white, but it'll get, as the saying goes, cherry red. And that's because the wavelength that it's producing from resistance is now moving upwards from infrared to near infrared to dark visible red to brighter visible red. So at that point, you go, okay, I can see it now. That's hot. I'm not going to touch it. But your body will feel the heat from it before your eyes start detecting the redness of it. You've learned how to exist in this environment where you can't visually see infrared, but your body can feel the heat from it or the warmth of the sun. There are things that your eyes can't see, but other parts of your body can sense.
The moon's going to go through Pleiades tonight.
Well, the moon is going to transverse through the Pleiades. It's not going to go through the Pleiades, but I understand what you're saying.
It'll appear.
Yes, it will occult, not to do with witchcraft, but it will occult the Pleiades because the moon's much closer than the Pleiades. Now, the Pleiades is an open star cluster that has a number of bright stars in it. The interesting thing will be if you zoom up on the edge of the moon, not the terminator, the light to dark part, but the actual outer edge of the moon, and you pick the part where the dark part of the moon is, if the moon's not full, then as the moon moves off of the Pleiades, you can use the starlight from one of those bright stars to illuminate the surface, the rough surface of the moon. There's a group that their focus is on occultations, and that's how they measure things. If you want to measure like the size of a crater along the edge of the moon, since you can't see it face on directly, then you can measure it based upon the light projecting over the edge of the moon to show you how wide the crater is.
Mm-hmm.
Okay. Any other comments or questions? Otherwise, I'll stop recording. Hearing nothing.